I'm Norman Wildberger, and welcome to 2012, this being January 1st. I've just come back from Coogee Beach, where I've had a morning swim and watched the sun come up. I think this year is going to be a very interesting year for this series, because we are going to move towards a very big challenge, that of tackling the deficiencies and the downright errors of modern mathematics. Modern mathematics doesn't really make logical sense. It does not work as a logical operation. It works on a lot of other levels, in terms of papers presented, seminars given, conferences attended, students given degrees, etc. But at the level of a logical discipline, modern mathematics is very, very weak, and in fact, there are such gaping holes in it that you could drive trucks through it. Now, it's very unpopular to say such things, and most people shy away from voicing their objections. The status quo is firmly entrenched in modern pure mathematics. But this year, we're going to try to give it a big push. Try to move it. Try to reorient it towards a more positive, fruitful direction, where the logical structure of the discipline becomes clear, with all kinds of benefits, not just for mathematics research, but more importantly, for mathematics education. Okay, so it's a big challenge, and we're going to have to change the tone of this discussion occasionally. I'm going to have to become a little bit more confrontational. I'm going to be honest, perhaps brutally so. I'm going to have to call a spade, and when things don't work, I'm going to have to be very clear about saying that. All right, so that's going to happen this year, and we look forward to confrontation, controversy, but interesting intellectual developments. Today's talk, we are going to talk about Laurent polynumbers, which are an interesting extension of polynumbers in the direction of decimal numbers being an extension of ordinary integers. So let's begin by just talking a little bit about our framework for polynumbers. We started off with natural polynumbers, and then we had integral polynumbers. We also had fractional polynumbers, and then ultimately rational polynumbers. Let me just briefly review the sequence that we went to get to the rational polynumbers from here to here to here. A natural polynumber was for us a list of natural numbers, like 3, 1, 4, a little square bracket on top of it there. And eventually we represented that in what we call standard alpha form, 3 plus alpha plus 14 alpha squared. So the polynumber P is here represented by this object which looks more like a traditional polynomial in alpha. Here's another one, Q equals 2, 5, which will be 2 plus 5 alpha. And then we move to integral polynumbers. And the official definition of an integral polynumber is very much like the official definition of an integer. Here, an integral polynumber is a pair of natural polynumbers. And we generally write the pair with this sign here, less sign, P less Q. So for example, this polynumber 3, 1, 14 less this polynumber 2, 5 gives us an integral polynumber, which effectively we write down as simply the difference between the various positions. So 3 minus 2 is 1, 1 minus 5 is minus 4, 14 minus nothing is 14. In other words, we're effectively dealing with lists of integers. And we write such a thing with polynomial notation with alphas, 1 minus 4 alpha plus 14 alpha squared. So that's an integral polynumber. So then when we have integral polynumbers, we can define rational polynumbers, which are essentially sort of quotients or formal quotients of integral polynumbers. Officially, it's a pair of integral polynumbers, a over b, So there's, for example, one polynumber integral is another polynumber integral. The quotient 1 minus 14 over minus 3, 2. We can also write it in standard alpha form this way. It's the rational function, sometimes called 1 minus 4 alpha plus 14 alpha squared over minus 3 plus 2 alpha. So it's an integral polynomial divided by another integral polynomial as a formal object. It doesn't have to be that this actually is divisible by this. We just treat this combination as a new mathematical object, just like we treated the combination 3 over 5 as a rational number, a new object built up from natural numbers and integers. Alright, these rational polynumbers are a very nice framework because the four main operations of arithmetic are available to us in this framework. So let's have a review of those operations just to make sure we all understand how the arithmetic of these rational polynumbers goes. So we're going to work with the standard alpha forms. Here is one rational polynumber, here's another, and let's add them. Adding them is defined the same way you add rational numbers. So what we do is we take the numerator here times the denominator there, and add this denominator here times this numerator here, and divide by the product of the denominators. When we expand this out, we get 14 minus alpha minus 2 alpha squared plus alpha cubed. So for example, the 14 comes about because the constant term is 2 times 1 here and 3 times 4 for a total of 14. The minus alpha term comes about because there's 2 alpha here plus 1 alpha here minus 4 alpha here, so a total of minus alpha, and so on. So once we've expanded these things out, put them in standard alpha form, then we have one integral polynumber divided by another integral polynumber. That's our answer. So this polynumber plus this polynumber is this polynumber. Multiplication, also exactly the same as with fractions or rational numbers. To multiply this one by this one, we multiply the numerators and we multiply the denominators. We expand each one of those separately. And please check that I've done the arithmetic right there. Alright, so good exercise, just make sure I've done everything correctly. So we end up getting another polynumber over another polynumber. That's how we multiply rational polynumbers. Once we have the primary operations of addition and multiplication, then the secondary operations of subtraction and division follow on roughly similar lines. So to take the difference between this one and this one, it's a lot like addition, except we take this times this minus this times this in the numerator, and the denominator is still the product of the two denominators. Then you can expand that out, check that I've done the arithmetic right. We get that polynumber in the numerator over that polynumber in the denominator. That's the difference of polynumbers. And finally, the quotient of two polynumbers, this polynumber divided by this polynumber, is what we get when we take this polynumber and multiply by the reciprocal of this one. So we multiply this over this by alpha squared over 4 minus alpha to the fifth. And then we expand that out and we get that thing there. So the rational polynumbers form a nice arithmetical domain in which we can add, multiply, subtract, and divide, and where those operations satisfy the same laws as they do for ordinary rational numbers. So this kind of domain of arithmetic is called in mathematics a field. There's another very important point of similarity between rational numbers and rational polynumbers, and that is the notion of equality. Both rational numbers and rational polynumbers have different possible representations. So a given rational number can be described in a number of different ways. For example, 2/3 is the same as 4/6, is the same as 6/9, is the same as -2 over -3. So there are many different representations of the same object. So the official definition, I remind you, is that the rational number a over b equals the rational number c over d precisely when AD equals BC. So for example, 147 over 252 equals 42 over 72. We can check that because 147 times 72 equals 252 times 42. You can compute that. They both turn out to be 10,584. And because they're both equal, that tells you that this rational number is the same as that rational number. Of course, another way of determining that would have been to reduce both of them. This one here, you can see that it has a common factor of 6. So if we divide top and bottom by 6, we would get 7 over 12. And with a little bit more work, you could also figure out that this can be reduced to 7 over 12. But this strategy of reducing both sides is not the best strategy in general. For example, suppose that you wanted to check that this rational number was the same as this rational number. It's not so trivial to reduce these fractions. You can try it by figuring out what is a common factor that we can divide both top and bottom by, and then doing the division and then seeing what additional common factors it has. That's a rather laborious procedure. In fact, it's much easier in general to check that this rational number equals this rational number by taking this times this, computing it, and then taking this times this and computing that and checking that they're equal. That's a little exercise for you to actually do that, to check that these things are equal. This is such an important point. I'm going to have to emphasize here, right, that although we have different representations for a rational number, we have this surefire, concrete, completely explicit way of checking whether two representations are actually the same. There's no ambiguity whatsoever. There may be some work involved, but that work involved is finite, it's completely clear, straightforward. We can tell whether one rational number is equal or not equal to a second rational number. If we were not able to do that, it would be very cumbersome to do arithmetic. Arithmetic would become vague and would become sort of open-ended because we wouldn't be able to tell whether my rational number was the same as your rational number. It's essential for us, if we're going to have different representations for an object, to be able to tell whether two representations actually are the same or not. That's a very important point. Please give that some thought. Okay, so the pleasant thing about rational polynumbers is that exactly the same rule defines equality for rational polynumbers. If these are integral polynumbers, and these are integral polynumbers, then this rational polynumber equals this rational polynumber exactly when this equality works between this product of integral polynumbers, I guess it's that one, and this product of integral polynumbers. So for example, this rational polynumber equals this one. We can check that because 1 minus alpha squared times 1 is the same as 1 minus alpha times 1 plus alpha. We can compute those two products and see that they're the same. Of course, another way of seeing this would be to recognize that here there is a common factor. The common factor is in fact the denominator. 1 minus alpha is a factor of that numerator, and the other factor is 1 plus alpha. So we can also sort of divide by the common factor to go from here to here. Here's another example. 1 minus alpha cubed over 1 minus alpha is the same as 1 plus alpha squared over 1. The reason is because this times this equals this times this. And you see, I suppose, the geometrical series formula occurring there. Or to put it another way, this one here is actually divisible by this one. And the common factor, if you canceled it, well, then you'd be left with this one here in the numerator there. Here's another example where the common factor business might be a little bit less obvious. Okay, so here's a good exercise to give this equality some thought. So these two rational polynumbers are equal. We both have something of degree 4 over something degree 2 here, something of degree 4 here, something of degree 2 here. It's not so obvious, perhaps, to realize that there are some common factors that can be canceled. To show that this equals this, straightforward way is just to take this times this, compute it, take this times this, compute it, then check that those two integral polynumbers are the same. If they are, we can deduce that these two are the same. Please have a go and check that as an exercise. So the arithmetic of the rational numbers and the rational polynumbers is very parallel. But the rational polynumbers are a much richer arena for doing arithmetic, with ultimately more consequences for mathematics. These two fields are the most important ones in mathematics: the field of rational numbers, the field of rational polynumbers. A lot of mathematics ultimately is concerned with the arithmetic generated by these two fields. Now, most pure mathematicians will look askance at this statement and say, well, no, the most important fields are the real numbers and the complex numbers. If you're a graduate student, you've probably been trained on automatic pilot to think of these as the two most important fields. Let me say very clearly, okay, these fields are not very important because they don't really exist. They are illusions. They are fantasy constructions. We could also say that they're jokes. They're hoaxes played on us by ourselves. They are really frauds. The theory of these fields just doesn't work as it's usually laid out in modern treatments. In fact, the modern treatments of these fields are very skimpy, if you find them at all. If you look in the ordinary calculus text, there's usually some initial discussion about what these things are. Notably, that discussion is invariably missing on any kind of detail. They're simply wishful statements presented that you're supposed to believe without any supporting evidence. Even if you look in more advanced analysis texts, you will see that when they come to trying to say clearly what these things really are, the logical structure invariably collapses. Now, if you're a graduate student, you probably find yourself skeptical about that because you know that there's 10,000s of mathematicians out there who all talk about real numbers and complex numbers on a daily basis. So you're thinking, well, how can Weilberger possibly be right? So here's a good little test for you. Okay? Maybe you think that you can simply write down a good presentation of, say, what real numbers are. If you have a spare weekend, you might try that. Okay, say, I'm going to write it down. I'm going to send this to Weilberger and see what he says. See if he admits that I know how to establish real numbers. What do you have to do? You have to write down exactly what is a real number. You have to write it down exactly. You have to describe precisely what the operations on real numbers are. You have to prove the laws of arithmetic that you want to hold for those operations. And to convince us, you should give plenty of illustrative examples. So here's how we multiply real numbers. You take this real number, you multiply it by this real number, here's how you do it, and the answer is this real number. And please circle your answer when you're finished. In a big red pen, circle your answer so we know exactly where it is so we can have a good look at it. If you try this humble little exercise, you will find something curious. That is not as easy as you first thought. That as you start doing it, you start thinking, actually that's a little bit difficult. I wonder, how do I actually do that precisely? Or, I see that I'm using words here that I haven't properly defined yet. I wonder if Wildberger is going to require me to define these words. Well, yes, he is. Okay. And then when you ask yourself, well, how do I actually define those things? You will find that, I need a prior theory of Euclidean geometry. Or I need a prior theory of infinite sets. Do I have such prior theories? Well, it's up to you. Do you or you don't? Well, if you don't, then you don't have a proper definition. Then you, along with your fellow mathematicians, are faking it. We're going to say a lot more about this. So 2012 is going to be the year in which we take down the fraudulent aspect of these supposedly fundamental frameworks. And you're slowly going to see that everything you can do with real and complex numbers, you can do with rational numbers and related constructions. Anything real that you can do with them, anything that's computationally effective, you can do in the rational framework. So a big challenge, very contentious. Don't accept the status quo unthinkingly. Okay? Put your critical thought caps on. All right, so let's return to something less contentious. We are now going to introduce Laurent polynumbers, which are analogous to decimal numbers in the rational number framework. So Laurent polynumbers are to polynumbers the same as decimal numbers are to regular numbers. It's the rough parallel that we're going to pursue. So the definition. A Laurent polynumber is a rational polynumber, P, which can be written as A over B, where A and B are integral polynumbers, with a denominator B a power of alpha, for some n, which is a positive number, meaning it could be a natural number, 1, 2, 3, 4, and so on, or it could also be 0. Which is to say that b equals 1 is included, because alpha to the 0 is by definition 1. So a Laurent polynumber is a special kind of rational polynumber. It's one where the denominator is either 1 or a power of alpha. So here are some Laurent polynumbers. 1 plus alpha squared over alpha cubed. Well, we can see that it's one integral polynumber divided by another integral polynumber, and the denominator is a power of alpha. So it is a Laurent polynumber. Okay, here have a look at this one. Alpha plus alpha squared over alpha squared plus alpha cubed. As it stands, the denominator is not a power of alpha. But this thing can actually be rewritten. This is also equal to 1 over alpha. So as long as we can rewrite the polynumber in another form, where there is a denominator which is a power of alpha, then the original is a Laurent polynumber. So the fact that this is equal to 1 over alpha means that this is a Laurent polynumber. This is obviously a Laurent polynumber. There's an integral polynumber divided by a power of alpha. Here, again, we can rewrite this because we can take out the factor of 1 minus alpha. Here, this is alpha cubed times 1 minus alpha. And 1 minus alpha is also a factor of the numerator. All right, so you can check that you can rewrite it by essentially canceling the factors of 1 minus alpha, and then you do get a power of alpha in the bottom. So this is analogous to what we were doing with decimal numbers, where we allowed something like 2 over 5. 5 was not a power of 10, but that fraction can be rewritten as 4 over 10. Once we rewrite it as 4 over 10, then there is a power of 10 in the bottom, and the thing is a decimal number. This is a Laurent polynumber because 1 is considered a power of alpha. And this one here, also it's in the category because this factor here of 1 plus alpha that's down here, you can check that's also a factor of the numerator. So you can rewrite this one to make it in this form. So a little bit of work there to check a couple of these examples to see that they're all Laurent polynumbers. Here are 3 examples of things which are not Laurent polynumbers. This one isn't because the denominator is not a power of alpha and there's no cancellation possible between here and here. So there's no way of making that a power of alpha. Here, it looks like there's a power of alpha, but it's got to be a pure power of alpha. That 3 is not allowed. The denominator has to be an integral polynumber. The numerator has to be an integral polynumber, so integers only, and that 3 is not allowed. This thing is not a Laurent polynumber because it's not even a polynumber. We're only considering ratios or quotients of polynumbers where the denominator is not 0. That was a condition of being a rational polynumber. Alright, so now let's introduce the Laurent form for a Laurent polynumber. This is analogous to the decimal form for a decimal number. So suppose P is a Laurent polynumber, A over B. So we can write it as some integral polynumber, A, divided by some power of alpha, say alpha to the k. And now we're going to rewrite this. We're going to introduce a new terminology or new notation. We're going to write this as alpha 0 times alpha to the minus k. This is simply new notation that we're introducing. Plus a1 times alpha to the 1 minus k. We're going to essentially subtract k from all the exponents of alpha here, all the way through up to the last one, which will be an alpha to the n minus k. So for example here, we have 1 minus 3 alpha plus 4 alpha squared divided by alpha. Then we subtract 1 from the powers of alpha in each of the terms in the numerator. Here is alpha to the 0. We subtract 1, we get alpha to the minus 1, minus 3 plus 4 alpha. And now let's introduce some notation for this Laurent polynumber that extends our original notation for an ordinary polynumber. So that was an ordinary polynumber, and now we're going to introduce the idea of the negative powers of alpha being expressed by additional numbers above the bracket. So this was the coefficient of alpha to the 0, this was the coefficient of alpha to the 1, alpha squared, alpha cubed, and so on if there were more. This is now going to be the coefficient of alpha to the minus 1. And then above it, alpha to the minus 2. And above it, alpha to the minus 3, and so on. As another example, 2 alpha squared minus alpha cubed over alpha cubed. That's a Laurent polynumber. We'll subtract 3 from all the exponents. 2 alpha to the minus 1 minus 1. And then we'll write that in this new notation as 2 bracket minus 1. That's the power of alpha to the 0. That's the power of alpha to the minus 1. So this is a lot like decimal notation, except that we're not introducing decimal digits to the right of the decimal point. We're introducing these negative power coefficients above the bracket. It's the direction that's analogous to the right of the decimal point. So it's entirely analogous to what we did with decimal numbers. All right, so let's have a look at some more examples. Here's a Laurent polynumber, 5 minus alpha to the 7 plus 3 alpha to the 11, all over alpha to the 9. Subtract 9 from the exponents of the alphas, we get 5 alpha to the minus 9 minus alpha to the minus 2 plus 3 alpha squared. And then if we're going to write that in our standard original form, starting with the highest power, there's 3 alpha squared. There's no alphas, there's no 1s, there's no alpha inverses. There's a minus 1 alpha to the minus 2, to the minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9. 5 alpha to the minus 9. Alpha plus alpha squared over alpha squared plus alpha cubed. Well, we can factor the top and bottom. We can cancel the 1 plus alpha. We can even cancel an alpha. We just get an alpha to the minus 1. And the notation for that one is this one here. There's also rather a fundamental, basic kind of new object. This is a lot like alpha, which was bracket 0, 1. This one is bracket 0, 1, like that. It's the inverse of alpha. If you multiply alpha times this one, you get 1. Alpha cubed over alpha to the 5th, that's the same as 1 over alpha squared, or then alpha to the minus 2. That's represented by 0, 1, 0. Notice that we're going to adopt a kind of a similar convention about placeholder 0 here, as we did for decimal numbers. We prefer to write 0.03 rather than just 0.03, so that 0 is sort of telling us that we have a decimal number there. Similarly, we're going to put at least one number below the bracket. So bracket 0, 0, 1. That 0 is technically unnecessary. It's just a convention that we're going to put it there. Here's another one, for example. And here is going the other way. If we start with something in this form and we want to write it as a Laurent polynumber in the more standard form, we write it out in terms of powers of alpha. There's an alpha to the minus 2, minus 3 alpha to the minus 1, 0 1s, and 2 alphas. And then to rewrite that, we would take the highest negative power out. That's an alpha squared. And then that would leave 1 minus 3 alpha plus 2 alpha cubed. Right, so make sure you understand how we go from there to there. Now it's pleasant that we can do arithmetic with these Laurent polynumbers just in their Laurent form. We don't have to convert them back into the standard form for a rational polynumber and do the arithmetic there and then convert back. So let's have an example of that. So here is one Laurent polynomial in Laurent form. In other words, written out as powers of alpha, including negative powers of alpha. And here's another one with powers of alpha and negative alpha. So to add those, the easy way of doing it is just to look for like powers and add them separately. So there's an alpha to the minus 3 here and here, coefficient of minus 3 here, coefficient of 5 here. Add them together, a total coefficient of 2. Alpha to the minus 2's, there's only one of them with a minus sign. Alpha to the minus 1's, there's 2 of them here and 1 of them here for a total of 3. Constant things, there's a 4 here, there's no constant term, so the 4 is there. Simple alphas, there's a minus alpha here, a 3 alpha here for a total of 2 alpha. Now that corresponds to the following computation with more traditional rational polynumbers. This thing here is just this rational polynomber. Minus 3 plus 2 alpha squared plus 4 alpha cubed minus alpha to the 4th divided by alpha cubed. That's the same as this one. And this one here is the same as this one. In this case, the denominators are the same, so adding them is relatively simple. We just add this to get that, and the denominator stays alpha cubed. If we were to convert this to its Laurent form, we would get immediately this. So this computation at the Laurent form level is reflecting the computation with the rational polynumbers themselves. But it's sort of quicker just to add powers of alpha like powers of alpha. And let's have a look at multiplication. So here is product of two Laurent polynumbers in Laurent form. And we can work just at the level of powers of alpha by multiplying term by term using the distributive law and then collecting like powers of alpha. So for example, 3 alpha to the minus 2 times alpha to the minus 1, that's 3 alpha to the minus 3. Alpha to the minus 1, how do we get that? Well, we get that with 4 alpha to the minus 1. That product there is 4 alpha to the minus 1. While this times this is minus 3 alpha to the minus 1. So we have 4 alpha to the minus 1 minus 3 alpha to the minus 1 for a total of plus 1 alpha to the minus 1. And please check that when we expand these things, collect all terms, we get this resulting Laurent form for the Laurent polynumber. Now this all corresponds to this more traditional computation using the standard form for the rational polynumbers. This one here is really the same as this one. This one here is really the same as this one. If we multiply these in the usual way, this times this, just ordinary integral polynumbers multiplied together, we would get this one, and the product of these is alpha cubed. And then if we took the Laurent form of this, you can check we would just get what we got up there. And a final comment, all of this discussion works equally well for row polynumbers. There's nothing special about Laurent polynumbers just for column polynumbers. Exactly the same story for row polynumbers. For example, 2 plus beta minus beta cubed over beta squared. That's 2 beta to the minus 2 plus beta to the minus 1 minus beta. And as a row polynumber, we're going to write this the following way. There's a power of beta here with a coefficient of minus 1 that's represented by that minus 1. There's 0 constant term. There's 1 beta inverse. And there's 2 beta to the minus 2s. So that would be a standard row polynumber. Now we're sort of adding decimal versions corresponding to higher powers of beta, but we're doing it admittedly going left rather than right for decimal numbers. And because they're row objects, we enclose both sides with brackets to minimize the confusion between where does this thing stop and another mathematical object begin. When we're writing things in long rows, we have to be conscious of the fact that it's easy to get mixed up in terms of adjacent things. So there's a new convention or an additional convention for row polynumbers that we don't use for the column polynumbers. And here's another example that you can check. Here's another polynumber. There's its Laurent form, and there's what it looks like in sort of the standard original form for the polynumber. We've now acquired a fair amount of experience with the algebra of polynumbers and their extensions, Laurent polynumbers. Next time we're going to start flexing our muscles and apply this framework to discussing the derivative. So it turns out that the derivative, as discussed in most calculus texts, doesn't actually require limits. It certainly doesn't require real numbers. The derivative is ultimately a purely algebraic concept, and it's best understood as an algebraic concept. So we're going to introduce the derivative next time in the context of translating polynumbers. This is something that we can do with polynumbers that we can't do with ordinary numbers, or rather doing it with ordinary numbers is complete triviality. Translating polynumbers is an interesting new development. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening, and Happy New Year.